3, 2, 1.
This is a shot of my ceiling, filmed at 240 frames per second by a flat, thin, stabilized pod that looks like a Pop-Tart. The pod contains a GPS tracker because my real goal isn't to film my ceiling, it's to shoot it out the side of a rocket as it reaches a 10-kilometer apogee. The pod will capture parachute deployment in slow motion, then fall several miles to the ground and be recovered after flight. Getting this to work was way harder than I expected, and I've already had to make a compromise. Keeping the pod pointed back at the rocket as it shoots out proved too hard for a completely passive setup. And we need the camera pointed at the rocket because I can't use a 360 camera for the reasons I covered in the last video. But to keep the pod stable, I think if I add a brass flywheel acting as a gyroscope, that might do the trick. I'm cutting this wheel out of brass because it's dense, easy to machine, and it looks pretty. I'm making it on the manual lathe from 1-inch round bar stock, and while I'm tempted to call this a reaction wheel, it's not. It's a gyroscope, and they're different. A reaction wheel changes speed to exchange angular momentum with whatever vehicle it's attached to. When the wheel spins up, the vehicle rotates in the opposite direction, so total angular momentum is conserved. A gyroscope also stores angular momentum, but it doesn't exchange it with the vehicle because it operates at a constant speed. Instead of steering by changing spin rate, it simply resists changes to its orientation. To rotate it about an axis perpendicular to the spin, the angular momentum vector must change direction, and that requires a lot more torque with a higher RPM. Like we covered in the last video, this is why a fidget spinner feels the way it does in your hand. A fast spinning rotor wants to maintain its direction, and in my case, it's going to keep the pod pointed back at the rocket. This brass wheel ended up around 30 grams, and I press fit it onto a 12-volt DC brushed motor. The first time I spun up, it vibrated quite a bit.
That doesn't sound great.
The goal here isn't perfection, it's just a proof of concept, so let's keep moving. To control when the wheel spins, I added a small, programmable timer rated for a few amps of current. You can think of this like an electronic relay, but it knows how to count. The motor draws a lot of current, so I don't want it running the entire flight. Ideally, it only spins during the short window when the pod actually needs stabilization. It's a little hard to see in this shot, but when the timer powers on, it lights up a red LED, and when the timer turns off, so does the LED. We'll talk about this more later, but the motor only really needs to spin around here, and if we limit the spin time, we can use a smaller battery. So I programmed the timer to delay the motor startup, wired both of those up to a battery, and gave it a test. The motor spun up and powered off at about the right time, but when I watched this footage back, I noticed the red LED takes kind of a long time to turn off. That's weird. Let's not think about why and just forget it. I loaded everything into a test pod without a camera, but before I could toss it around, I noticed the motor sounded unhappy.
That does not sound good, dude.
The motor had been vibrating a lot, and the shaft was rubbing on the plastic at the rear of the housing, melting the plastic and enlarging the hole.
Wow, man. That's not good.
I figured this cheap little motor was not designed to carry a heavy brass flywheel and get thrown around while spinning at high RPM. So I tested another DC motor with a rear support made of metal, but this one didn't spin the wheel nearly fast enough, so I treated it like a mic and I dropped it. I'm not gonna drop this mic here. I have a bunch of stuff to film today and I'm really worried that I'm gonna break it, but like spiritually, I'm dropping the mic. Next, I tried a plastic wheel with a replacement for that original motor. It's 3D printed out of PLA, and while it's obviously lighter than the brass wheel, maybe it would wear the motor down less. It worked in the sense that it gave some stabilization, but this still felt too weak. There's a lot of movement here. The pod would oscillate around a stable point, but even tiny disturbances when I tossed it up would knock it for a loop. I should have stuck with the brass wheel. So this time, instead of committing to one size, I made 2 more brass wheels, a small one around 5.5 grams and a medium wheel around 15. These two technically worked when I tossed them in the air, but the small and medium wheels behaved too much like the plastic one. They didn't have enough authority to truly stabilize the pod, so I tried remaking the 30-gram wheel, but this time much more carefully. I worked hard to keep the central hole perfectly centered to reduce vibration, and once I spun it up, it felt much better than the previous large wheel, at which point I realized that it was vibration that had melted the back of that previous motor. The problem was less about the wheel being heavy and more about it being imbalanced. And in fact, if I look at this footage from the first wheel lathe work, I can see how this happened. the center drill walks slightly off axis when piloting the central hole, so that first wheel was doomed from the start to cause tons of vibration. The new 30-gram wheel provided a lot more stability for the pod, and after tossing it around quite a lot, I felt confident that this would do the trick to keep the camera pointed in the right direction when it shoots out of the rocket. Now, I mentioned earlier that I only want the motor to spin for a short period of time, so I set the timer to turn it on at 20 seconds and turn it off around 70 to 75. But the motor isn't the only thing that needs to run on a timer, the camera does too. Sorta. It's weird. Okay, if you're watching this video, I'm gonna trust you with something. I'm gonna trust that you're interested in all of the really weird details. I have a very strong urge to not talk about this for the sake of YouTube retention, but if you're watching this, I'm trusting you wanna know. So you and me, we're gonna go on a little journey. Lock in. To save battery, the GoPro is powered on at liftoff with a pull pin. We'll talk about this more later. I want the GoPro to start recording quickly after launch, but not immediately. To understand why, I have to tell you about file formats. GoPros record video files as MP4s. That's a little risky. It's riskier than something like an MKV, which is the best video file. Let's think of an MP4 file like a book. Before it becomes a book, you're writing page by page, and you end up with tons of these, but they're not super organized. So before it becomes a book, you number all the pages, and then you write a table of contents. If I handed you all these pages without the table of contents and without them numbered, you'd have a really hard time reading this book. For an MP4 file, the camera is logging all the frames of data as it goes. And in the last video, we covered how interframe compression means that this isn't recording lots of still images, it's a whole mess of file types. Some of them are keyframes, some of them are interpolation frames, and all those frames of varying types are kind of like all the pages here. Some of these pages are chapter headings, some of the frames are keyframes. Just like how when your book is finished, you write the table of contents, when your clip is finished, the GoPro writes a table of contents for the MP4 file. The MP4 table of contents contains information about frame rate, playback speed, frame types, etc. And so let's say in the middle of recording this clip, I pull the battery out and the GoPro doesn't have a chance to record that table of contents. If that last bit isn't recorded, the clip becomes corrupt and it can't be played. There's no table of contents, there's no numbers on the pages, you can't read the book. Now, sometimes you can recover that data, but not always. GoPros do this cool thing where when the camera powers up, it looks at the SD card, and if it sees a corrupt clip in there, it'll try to repair it. I don't know exactly how they do this. I imagine it's looking at the last known settings on the camera and maybe some information in the file, but the process of repairing these files can take 5 to 10 seconds, and during that time, the GoPro can't record a new clip. So I need to build in some margin there. That means the camera needs to power up at launch, wait 10 to 15 seconds, then start recording. Filming at 240 frames per second will capture the rest of the ascent and deployment. Then I'll let it roll for another 60 seconds before commanding it to stop recording. That might seem weird, but there's a good reason. The most important thing for this whole project is capturing that deployment at apogee in a properly closed file. If the camera is still recording when it slams into the ground, there's a big risk that a battery disconnect will corrupt the file. And even though GoPros can sometimes repair the file at startup, it's not a guarantee, so I want to close the file while it's still in the air. Then, later, near the expected ground impact, I'm going to command the GoPro to record again to see if we can capture that impact. This is going to be in a separate video file, and if that clip gets corrupted, who cares? I have 1,000 shots of GoPros hitting the ground. I don't need another one. Now, speaking of batteries, let's talk power budget. My original plan was to run everything off a 300 milliamp hour 4-cell LiPo. The usable capacity of that is probably like 85%, so let's call it 255 milliamp hours. The gyro motor draws an average of 300 milliamps at 16 volts, and the GoPro draws about 550. Let's be generous and assume we're running everything for 2 or 3 times as long as we need to. I'll say I want to run the wheel for 3 minutes and the GoPro for 15. So the wheel will burn like 15 milliamp hours and the GoPro will burn 140. That puts us at 100 milliamp hours of margin. The timer won't use enough power to care about it, but the other device here is the tracker. The tracker has a maximum power draw of 200 milliwatts. That's milliwatts, not milliamps. The reason I'm giving it to you in these units is that we have a little bit of a voltage issue. The Reprix tracker I'm using can tolerate a pretty wide range of input voltages, all the way up to 16 volts, but a 4-cell LiPo, when charged, is at 16.8. Maybe there's some margin in the stated spec for the Reprix, maybe we could push it to 17, but since we're using a brushed DC motor, that's going to be really noisy on the power lines, so it might spike the voltage even higher than 17. A 4-cell LiPo is just a little too much voltage for this tracker. So, I had an idea. What if we powered the Reprix off of one of the balance leads? If we pull current through 3 cells instead of 4, we're going to drop that nominal voltage down to 11.1. In theory, and definitely in practice, that will slightly unbalance the battery, but it should also get fixed with every charge. And at 12 volts, the Reprix is only going to draw 17 milliamps, which should be within what a balance lead can tolerate current-wise. This is pretty sketchy. I don't feel super proud about it. I would like to move on and talk about something else. In CAD, I made the pod larger to deal with the space issues I was having. Getting everything to fit in here was really tricky, so we're using the full door area for the pod now. Speaking of the door, I mentioned in the last video that my plan was to make the door out of acrylic, and to do that I used the sponsor of today's video, PCBWay. I thought that acrylic would be nice for this door so we could let some light in to help expose the camera. And while I could make it myself, I've machined acrylic before, this is one of those things where it's simply not worth the time for me to do that. Thankfully, PCBWay helped out with their machining service, which can do all sorts of materials: aluminum, titanium, steel, even composites like carbon fiber or FR4. They also offer 3D printing services for plastics and metals, and sheet metal, and injection molding. This is in addition to PCB prototyping and assembly, so pretty much if you want something manufactured, they probably have a service for it. PCBWay offers fast turnaround times, and their online quoting tool is super helpful for getting a rough estimate on project budget. The acrylic doors they made came out within tolerance and with a beautiful finish, and while this part didn't make it onto the final build, they actually built something else that I'll tell you about later. If you want to experience the magic of not having to make a part yourself, you can do that by clicking the link in the description. That's going to get you a real nice discount from PCBWay, and I'm so thankful to them for sponsoring this video. And with that covered, let's talk cameras. For the camera, I switched to a Flywoo GoPro Hero 12 setup. I used to rely on the GoPro Hero 10's Bones cameras, but they stopped selling those, and the Flywoo builds are 1,000 times easier to tear apart. This version already includes a board for battery elimination, so it's easier than tearing apart stock GoPros myself. I added a really long ribbon cable from Red Kite drones so that I could place the lens where I needed it inside the pod. The orientation of the sensor versus the board means the cable needs to do some real Mobius strip nonsense to keep things pointed the right way. I started testing GoPro Labs commands using the Hero 10 Bones. The Hero 12 is quite delicate here, so I want to mess with it as little as possible. I've talked about GoPro Labs on here before, but it's the reason we're picking a GoPro and not another brand of camera. This is not sponsored in any way, but GoPro did something really cool here, so now you're gonna hear about it. GoPro published a whole programming language that you can use to add a wild amount of functionality to these things. Using plain text that's represented as a QR code, you can change all the normal settings on the camera, plus a bunch of extra stuff, like logging sensor data, recording higher bit rates, and running custom scripts. The GoPro actually has an IMU inside it to help with image stabilization, and that turns out to be very, 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 very useful. This is foreshadowing for a future video that you don't know yet, but really useful data in there. Anyway, my original plan was to use this IMU to detect the acceleration from launch and have the camera start recording on its own. But as I was testing this, I found that even when the camera was just idling, it drew too much power. We'd need a much bigger battery or a power disconnect. And I already need to power on the timer for the motor at launch, so why don't we just hook the GoPro up to that and run the GoPro sequence off of that power on time. These commands can look like gibberish, but they're not too hard to understand. Let me break it down. When I wrote this into the script, I kind of imagined that I'd have two hands free, and then I started saying, can we move on? Can we move on? Can I be done? Okay, moving on. This command is mwake equals 2. Each new command starts with an exclamation mark, and the first letter is M, which tells the camera to store the following setting in permanent metadata, so the command will persist after we power cycle the camera. The command itself is wake equals 2, which tells the camera to boot up anytime power is applied. To program the camera, you just point it at the QR code. It reads that code as the plain text it represents, and it gives you a few blinks to confirm the setting was read. Now let's do a more complicated one. There's a lot going on here, so I will actually break it down without dancing. First, we have M, so we're storing in permanent memory, then QRDR, which is the QR read mode, and 1, which allows QR codes to be read even when the camera is recording. Then a new command, M, permanent memory, boot equals, which tells the camera to do the following action at startup. That action is L, which is the command to load a script, and auto record is a script that will be on the SD card. But we have to actually make that script, so the new command save saves a script with the name auto record, and then the contents of that script is the new command of S, which is the start recording right now command. So this one QR code sets the QR read mode, tells the camera to load the auto record script on startup, then creates the script, and now every time the camera powers up, it's going to start recording immediately. And since we use that mwake command, it's also going to power up on the application of power to the input. Like, we don't even have to hit the power button. Once power is just applied to the GoPro, it will wake itself up, boot, load the script, and start recording immediately. Programming the whole script to record at the right times and with the right settings took a long time and a good amount of troubleshooting. One of the big problems I ran into is that while I had run all the programming tests on the Bones camera, the Flywoo camera wasn't working with the exact same commands. Initially, it looked like the camera was mad because it wasn't getting enough power. The battery elimination board essentially runs the camera on USB power instead of battery alone, which the camera is not so thrilled about. This should have been fixed with the TUSB command, which tells the GoPro to chill out and just be cool if we're on USB power, but that didn't work either. The breakthrough came from a forum post several years ago about a command that wasn't listed in the lab's documentation. Nake equals 1. Apparently, it's used for internal troubleshooting at GoPro, and it makes the camera behave as if it's naked, i.e. when there's no screens attached. It seems like this is the key difference between the stock software shipped with the Hero 10 Bones and the Flywoo Hero 12, which, by the way, did work fine out of the box, but you do have to install GoPro Labs on new cameras, and after installing Labs, all those settings like Nake equals 1 go back to default, and so that seemed to break the camera. Also, unrelated, I completely bricked one of these cameras in this process. You do have to install Labs, and it is definitely possible to mess up this process. The camera is stuck in a boot loop. I have worked for 2 days to try to get it fixed. It's a lost cause. I could never have guessed just how hard this problem would be to solve, but usually in big projects there's like one big issue, and then the rest of it is smooth sailing. So thankfully, this should be our one big issue, the rest of it should be easy. Long pause. Oh I wasn't supposed to say. Once the GoPro programming worked, I started to make the camera physically robust. I potted sensitive areas in epoxy, especially around ribbon cables and vulnerable board sections. Then I did something a little extreme. I wrapped the most sensitive portion of the camera board in several layers of fiberglass and epoxy. Then I built dams around the SD card area so I could reinforce that region even more. The goal here is really simple. When this thing slams into the ground, I want a very stiff structure that's going to protect the SD card. If the SD card flexes a little bit with the whole PCB, it's going to break. A cracked SD card is a dead SD card. I have run this experiment enough times to know that. The theory here is that we should make the GoPro very strong, especially around the SD card, but we're also going to mount this with just a few dabs of hot glue within the pod itself. The idea being that the energy of impact will be absorbed by breaking those hot glue joints, while the internal structure of the GoPro is strong enough and its own mass is low enough that the energy of that impacting the inside of the pod won't be that large. It's like a much worse version of a crumple zone in a car. With the fiberglass layup, I realized the timer was going to have trouble fitting inside this pod, so I used a Dremel to remove the casing of the timer to expose the PCB, then conformal coated that so we didn't get any shorts. This made it much smaller and it shouldn't affect the function. I gave the GoPro one final programming with this QR code, and this specific one includes a lot more detail about the exact settings I want to use. Then I started wiring everything up. To power on the pod, I initially used this spring-loaded microswitch, with the idea being that we'll pull a pin out of the pod and the microswitch will spring open, powering on the setup. I hired a professional artist to draw out this wiring diagram. The microswitch goes here, this is the GoPro, timer, motor, and the GPS tracker. The tracker is powered on by plugging in the battery itself, and the GoPro, timer, and motor begin their sequence with that microswitch. At this point, I've tested each of these devices independently, but it's time to wire them up and perform integrated testing, which is a really important style of testing. If you don't perform integrated testing, you will often regret it. So with the timer programmed, the GoPro working, the motor and tracker hooked up, I connected it all to the 4-cell LiPo and gave it a test. And the sequence mostly worked. The GoPro started recording at the right time, the wheel spun up at the right time and then down, though I noticed that I had programmed the timer to run for way too long. And, there's that slowly dimming red light again. That's kinda weird. I wonder what that's about. Anyway, I reprogrammed the wheel to spin down after 35 seconds, then ran another test. But this time, after the wheel spun up, it never stopped. And the red light stayed on too. I had a feeling here that the flywheel was making it more difficult for the timer to shut the motor off, so I removed it and tried again. This is a really interesting problem, and one that I kind of hate. This is a brand new motor, but there's no load on it. There's no flywheel. Okay, we're powering up. Okay, it won't stop. It should stop after 5 seconds, and it doesn't. Okay, so this tells us something. I'll be honest, I don't know exactly what it tells us yet, but it tells us something. My next thought is that the motor was drawing too much current and exceeding the rating of the timer. But the timer is rated for 5 amps, and the motor only drew 1/5 of that at peak, and 1/10 of that on average. It seems to me that once there's a little bit of load on the line, we can't shut it off. Still confused, I let it run again in the same setup. I do not see this thing shutting off. Okay, alright. He's scared. He doesn't like this. Okay, Pumpkin. Okay, we don't like the sound. I don't like that this isn't working, and this young man doesn't like the sound of it. We're both unhappy for different reasons. In a way, we're unhappy for the same reason. We both wish it made less sound. I think for him, he'd love if it never turned on, but for me, I'd love just a short duration, and I can't get that, and I really don't want to break out the scope. In testing, I noticed the timer was able to turn off when there was no load connected, but as soon as the motor was attached, it had trouble. It's having the motor attached that creates a problem, and I bet the problem is that when it tries to remove power, there's a little bit of current that stays. Is it back EMF? It is back EMF. When you spin up a DC motor, the speed eventually plateaus because of back EMF, which means the counter electromotive force, which isn't even a real force. With the motor spinning, the coils whip past the magnets inside, and that generates a current in the opposite direction of the current driving the motor. So your battery's trying to spin the motor one way, and the back EMF works against it. The faster the motor spins, the stronger that force. Eventually, these two forces equalize, and that's your maximum speed. But when you remove all of that forward current from the battery, the only thing you've got left is the back EMF, and that keeps going because it's from the rotation of the motor. So all that back EMF current is going straight into the timer. And I have a hunch that the timer's not thrilled about this, so what if we just prevent current from going in the other direction? We can do that with a diode, and since I keep all of my old PCB components, I found an old Schottky diode from one of my old Ava boards that I soldered up to the motor circuitry to do just that. A diode will let current go one way, but not the other, so I hooked it up to give it a test, but this didn't work. I'm gonna skip past all the troubleshooting and just tell you that I fried the timer. I believe this happened on one of the first times I spun the motor up with it, and through checking the datasheet, I eventually figured out how that frying happened. But we do not have time for every single rabbit hole. I'm sorry. Thankfully, I know myself pretty well, which means I usually buy a spare for these projects. So I programmed the new timer, hooked that up, included the diode in the circuit, and to make a very long story short, I have never experienced this issue again. This process was really frustrating, and it's weird that there were two big issues in this project. Usually there's just one, but thankfully everything works now. It's a wonderful feeling knowing that for real this time, all the hard problems are done. Didn't say long pause this time. Getting pretty good at this. I should start a YouTube channel. With the new timer, the wheel finally turned on and off when it's supposed to, and now it's finally time to integrate everything into the camera pod. I potted the back EMF diode in hot glue, then began tacking down cables to make sure everything would fit inside. Since this is a prototype, I'm kind of figuring this out as I go. I knew I'd have some changes in the project, so I didn't spend too much time in CAD. I just took rough dimensions and trusted I'd find a way to make everything fit in there down the road. What can't move around in the pod is the DC motor. It's one of the truly fixed items inside, meaning I can't move it. But actually, in a way, I still can. It's mounted on this freestanding arm to try and dampen the effect that vibration from the motor might have on the camera sensor. That's also why it's mounted physically as far from the sensor as I can get it. As for power, I eventually figured out the 4-cell LiPo was slightly too big, so I found a spare 3-cell LiPo with the same capacity to put in its place. This slightly reduces the margin that we have in the power budget, but it gets rid of that really sketchy balance lead thing we were doing for the GPS tracker. Now we can pull current for everything directly from the high current leads on the LiPo. Ultimately, this ended up saving space in a few ways. I added a toggle switch sticking out of this little window, which will be used to power on the timer, motor, and GoPro at liftoff. I was initially going to use a micro switch here, but this proved a little too bulky and annoying to work with. The switch will start the whole sequence of when to spin the wheel up and record on the camera, and we'll flip this switch using a breakaway pull pin. The pull pin is made of TPU, a flexible 3D printable plastic, so it slightly grips onto the switch, but it lets go with enough tugging force. Before flight, I also added a little ramp-like object ahead of the switch to prevent the Mach 2 airflow from having too much of an influence on it. In theory, that airflow should just be pushing the switch into the on position, but this felt like a safe bet in case that flow was strong enough to damage the switch. But with this, we're finally out of the weeds on big problems to troubleshoot. So I gave the pod a power on to give it a quick test. The GoPro started recording, the wheel spun up, the wheel spun down, the GoPro stopped, the entire sequence worked. And just for kicks, I took the SD card out of the GoPro to double check that all the footage on the GoPro looked good. I put it in my computer, I watched the clip back, and I bet you thought that was a setup. No, the footage looked great, it was totally fine. And then the motor spun up. This isn't a problem with your phone or computer. This is an actual clip from the SD card playing back exactly as it was written by the GoPro. There are glitches everywhere. Huge lines horizontally, frame tearing and desync, several frames have a crazy hue, and there are periods where hundreds of frames are lost at a time, making it look like the video stopped playing. It hasn't, your video player is working fine, that's just exactly what was written onto the SD card. I hadn't been checking the GoPro's footage since adding the DC motor to the power bus, and when I went back through older clips of when that happened, the same issues popped up. The sensor had a piece of blue tape over it, and the components weren't jammed into the pod, but we're seeing the same problems. There's a good clue here, though, which is that they only show up when the motor is spinning. Actually, I should be more specific. They only show up when the motor is powered on. My first guess was that these glitches were coming from the electrical noise generated from driving the DC motor. To deal with this, I started by using what I had on hand. I added electrolytic capacitors across the motor leads to stabilize noise, but they didn't help much. The glitches weren't going away, which is disappointing, but it does give us a clue. Capacitors can help stabilize a power bus, but not all capacitors work the same. Electrolytic caps are slower to respond than something like ceramic capacitors. So if the noise in your circuit is very high frequency or really fast, electrolytic caps aren't going to do much to help. I broke out the analog scope to get a better sense for what kind of noise we were seeing on the power bus, and yep, they were pretty fast spikes. So I overnight ordered a pack of ceramic capacitors to give those a shot, but in the meantime, I'm impatient, so let's throw a bunch of things at the problem. I went through all my old PCB projects to find inductors, ferrite beads, other ceramic capacitors meant for surface mount applications. The inductors in particular were helpful, noticeably reducing the noise but not killing it completely. Then early the next day, the ceramic capacitors showed up so I could start messing around with those, and they are made by BoJack Horseman. I don't know. What? Most of this testing was done after I had removed the camera from the pod itself. It's all hot glued in, which means a little bit of isopropyl alcohol releases these bonds easily. I also took this opportunity to power the camera and wheel off completely separate power supplies and found that the glitches only showed up when they shared a battery. That's great to know for future versions of this camera pod, but I don't have enough space inside this one to fit a second battery, so we gotta make it work off of one. Unfortunately, the caps and inductor alone were still not enough, so I added an RC circuit to filter the noise even further. With each of these approaches, I measured success by how many glitches I could count by watching the footage back. A lot of this process was essentially me throwing things at the wall to see what stuck. I'm pretty far from an electronics expert. I just have access to the internet and a burning desire to solve this problem. After several days of going back and forth, I had nailed down a combination of inductors, resistors, and capacitors tuned to eliminate the noise in the circuit, or at least enough to keep glitches to a minimum. I figured I could tolerate 1 or 2 errors in the clip from Apogee, and we could just use this as a lesson about the next version. So I took all of the delicate parts and loaded them carefully back into the camera pod, then re-hot glued everything into place. Crossing my fingers as tightly as I could, I powered on the setup and let it run through the sequence. Afterward, I checked the SD card one last time to see if the glitches were gone for good.
Spin up.
Oh my god, it's worse. Ah, it's so bad. It's really bad. It's worse. Yay! I am having so much fun! At this point, I knew it wasn't just bad filtering contributing to these glitches. I had addressed that with all of the electronics outside the pod. The only thing that changed between the clean bench test and the glitchy in-pod test was the physical position of everything. So once again, for what feels like the 100th time, I used isopropyl alcohol to remove the hot glued components from the camera pod to troubleshoot. And when I pulled the GoPro out, I noticed something. This is a long custom ribbon cable connecting the GoPro sensor to the GoPro main board. It is unshielded, it is much longer than the stock cable, and it is really close to this yellow wire. This wire heads straight from the timer to the DC motor. It's got a diode in there, but we're not going to count that. The cable's unshielded, so it's pretty easy to mess up those signals, and by running the yellow wire right by them, I had been inadvertently injecting glitches in between the sensor and the recording board. There were real power filtering issues too. This wasn't just proximity. That's why it was helpful to add the capacitors and why we were able to eliminate all the noise on the bench test. But once integrated into the pod, there was also noise coming from the proximity of all the electronics to each other. So the only thing I changed is I bent this yellow wire down. Then I reloaded everything into the pod, powered on the setup, let it run through the sequence, and then checked the SD card one last time to see if the glitches were truly gone for good.
Spin up.
I don't think I see any noise. I think I did it. This is the dumbest. Since doing this, I have never seen the glitches return. Some combination of filtering obviously mattered, but so did the cable routing inside the pod. This is also where it became painfully obvious that choosing a brushed motor had been a mistake. A brushless motor would have been much cleaner electrically, but by that point, redesigning the entire pod around a new motor didn't make sense. This was a problem I could band-aid for this version and solve it properly in the next attempt. I mean, there's also an argument for like nothing is more permanent than a temporary solution, but this is a YouTube channel. I can do whatever I want. Once the electronics were stable, I brought the pod outside and let it sit powered on for several hours. I wanted to confirm that it could survive a long wait on the launch pad, keep GPS lock, and still behave correctly once the launch switch was triggered. That all looked good, so I moved on to full deployer testing. The deployer uses a high torque servo at the bottom and 2 springs on the side tied together with a zip tie. When the servo moves out of the way, the springs launch the pod outward. I first tested this with a mass equivalent dummy pod instead of the real electronics, just to avoid destroying the real unit while dialing in the mechanics. Next, I want to know how fast this thing is shooting out.
3, 2, 1.
By filming the pod as it deploys and measuring how far it travels across a known number of frames, we can estimate speed.
3, 2, 1.
For instance, here, the pod is traveling 1.4 meters over 12 frames of video shot at 24 frames per second, which means it's roughly at 2.7 meters per second. That number matters because it tells me how the shot will be framed during drogue parachute deployment. If I know how fast the pod leaves the rocket, I can better predict how long the rocket needs to wait before deploying the drogue parachutes so that it's entirely in frame. I'm neglecting drag and airspeed as part of this math, but it's at 10 kilometers, the air's pretty thin, it's not going very fast. I don't think that'll make a meaningful difference. To simulate the most realistic deployment I could before flight, I clamped the deployer to a beam in my house about 12 feet above the ground, then started ejecting the pod downward into a padded landing area. I set up pillows and blankets on the floor as a backup, and then a blanket draped over a few chairs as the primary way to slow it down. The blanket removes most of the energy from the falling pod through slower deceleration than pillows alone. I started by ejecting the dummy pod, and after that looked good, I moved on to the real pod. I loaded this thing into the deployer, powered it on, and then once the wheel spun up, I moved the servo to deploy it. The whole thing happens super fast, so now I finally get to show you why the slow motion is so important. I'll start by showing you the clip in real time. That's super fast. Let's see it one more time. Okay, now imagining this is a 360 camera, we wouldn't be able to slow it down much from here, since most of them can't do a lot of good slow motion. The resolution of a 360 camera also wouldn't matter, you just don't have enough time to appreciate what's going on. And programs that try to fake slow motion by interpolating between frames need much closer movement to actually work. Now, some 360 cameras can do 60 FPS, which would play back at 40% speed. This is certainly better, but I still don't think you have time to appreciate that view, and that is why the pod is filming at 240 frames per second. 240 FPS played back at 24 FPS allows me to slow the clip down to 10% speed. Honestly, this footage is way cooler than I expected. It's not even filming the rocket yet. I just think it's so beautiful how slow and stable it is. Seeing this little pod fall away at 240 frames per second makes all of the development worth it. This motion happens way too fast for a 360 camera to capture, and the shot only works at a high enough frame rate and resolution. Of course, this is only going to work if the pod is actually stable, so after running some clean deployments, I started disturbing the pod with compressed air as it fell. The gyro wheel stabilizes pitch and yaw, but it doesn't directly stabilize roll, so while the pod is locked in looking back at the deployer, it's free to spin on the roll axis, which frankly looks even cooler. Like, I'm not trying to induce roll, but a little bit of roll is good. To run a more intense compressed air test, I shot the pod as soon as it deployed and got the nozzle as close as possible to kick it really, really hard. This gave the pod a slight nutation behavior like we saw earlier in testing. That's that sort of corkscrew motion. It's a mix of the gyro wheel being off-axis combined with the effects of gyroscopic precession. Importantly though, it's still looking in that general direction the whole time. Even with disturbance, I should still be able to capture drogue deployment, which is what matters to me most here. One of the early deployment tests revealed that the gyro wheel was slightly rubbing against the door, so I shifted the door outward to make some room. Then, during a later test, I noticed that after landing, the motor turned off much sooner than it should have.
Uh-oh. Why did the motor die?
Given how much troubleshooting I have done on this so far, I was terrified. The sound of this thing spinning down was just a wave of dread, as I imagined that something had probably burned out in there, and I would need to remove all of the electronics again. And then I'd have to do another one of those bits where I'm like, oh no, one more big problem. Luckily, upon closer inspection, one of the leads had snapped off of the motor. Sort of. The wire broke not on, but near its solder joint, which is strange, because there's nothing around there that should cut it. And it's not a super clean break. I mean, both ends are kind of pointy. It seems like it just thinned out. The shape of this joint gave me a hunch that it might be induced by vibration. To figure out if this was true, I repaired the joint, then set up cameras to film the pod in high speed. My theory is that if we see a ton of vibration, we can be pretty sure that the vibration fatigued the wire and snapped it. Sure enough, when I filmed the pod at 1000 frames per second, I could see that the motor itself was shaking violently. My vibration isolation mount, the little arm holding the motor at a distance, was actually making the vibration worse instead of better. A poorly tuned vibe isolation system is worse than having none at all, and that's exactly what happened here. So I resoldered the joint, added glue to support the wires, and then abandoned the isolation mount altogether. I dumped hot glue around the motor to lock it in place, and the issue has never come up again. And the vibe isolation wasn't even needed in the first place. I can spot no rolling shutter or artifacts from the vibration that the pod feels when the motor is rigidly mounted. After fixing the motor mount, I ran several more deployment tests to try and disturb the pod as much as possible. The worst case result isn't beautiful footage, but it's good enough for a prototype. There's some visible motion and nutation, but the shot survives. For a version 1 prototype with a camera, tracker, and gyro all in this tiny package, I'm counting that as a win. As I looked at how cool these shots are, I realized very quickly how devastated I would be if I didn't get the footage from this thing. I'm really worried about a cracked SD card on landing, so as a last-minute addition, I tossed a streamer on this. There's not enough room for a parachute, at least in this version. I've used all of the available volume with wires and hot glue. So instead, I folded a streamer to fit around the outside of the outer mold line in this indent. The streamer fits in this cavity, and it's kept there with Scotch tape that I wrap around the outside. I use these little pieces of paper to prevent the Scotch tape from sticking against the streamer so it can pull out really easy. And then for flight, my plan is to leave about 1 or 2 inches of streamer hanging out. That'll catch enough air and it'll pull the rest of the streamer out. That way, the streamer isn't front and center in front of the camera for the one shot we want, but once the pod starts falling fast enough, it should pull itself out. It's a little goofy, but I think it works, and I ran a deployment test to confirm that the Scotch tape didn't ruin or change the deployment speed much. Okay. The streamer should definitely help, but it's hard to know how much until it actually flies. My best estimate right now is that without the streamer, the pod's gonna fall at 20 to 30 meters per second. And my guess is that with the streamer, we'll get closer to 10 to 15 meters per second. The real number of descent speed is gonna depend on how the pod orients itself in flight. And what I've been doing is averaging the area for each side and assuming it's a flat plate. There's a ton of assumption in these numbers. I wouldn't even call them my best guess. They're just like a guess. The next step before flight is to build a nose cone that we can actually shoot this thing out of. That video will be out soon, but if you want all the behind the scenes on how this build went and the flight itself, that is live on the BPS Patreon right now. For $5 a month, I publish videos every 2 weeks here showing you what I'm doing in real time. And if you just can't wait for the public videos, there's a link in the description down below. Thanks a ton to the folks who support over there, and thank you to you for watching. My name's Joey B. May your skies be blue and your winds be low. Goodbye. Why am I doing a thumbs up? That's goodbye. See ya.